All right. A very warm welcome and good morning, all of you. My name is Anmol Sachdeva, and the topic for today is understanding and implementing recurrent neural networks. So before starting, let's first see an example. If we are reading a book and it has, say, 5 chapters, we are on chapter 1, we have read that, we are going to chapter 2, we are starting reading it, but suddenly we forgot everything that was there in chapter 1. So how will we be able to understand chapter 2? It means short-term memory plays a very crucial role. On that motion, I would like to start with the recurrent neural networks. So Martin has already introduced me. I'll be skipping this. Prerequisites are you should be aware of Python language. You should have a decent knowledge of artificial neural networks and elementary linear algebra. So recurrent neural networks can be thought of as the neural networks which persist information, and we can think it of as sequential processes basically influencing decisions. So in contrast to the traditional neural networks which don't persist information, recurrent neural networks are having this advantage over those. So we can think recurrent neural networks as the networks having loops to themselves. I'll be explaining the architecture now. And these are one of the most complex supervised deep learning algorithms we have today. So consider a normal neural network, and it has many layers. X0, X1, X2 is basically the input that we are providing to the layer. A is a hidden layer. So the input from X0 goes to A, and the input gets transferred from one hidden layer to another hidden layer. Simultaneously, it gets transferred from the other hidden layer to the next hidden layer. And we can think it of squashing this thing that you see on your right-hand side into the thing that is known as the vanilla RNN. That means it is having loop to itself. RNNs can be of many architectures. The first one is one-to-many architecture, in which you provide one input and you can get many outputs. So you can think of, say, you provide with an image and it provides with certain caption. So an image is mapped into caption of, say, 5 or 6 words. So it is one image getting mapped into 5 or 6 words. That is one-to-many transformation of RNN. Likewise, we have many-to-one. So many-to-one can be thought of as, say, we are having video frames, and we are generating text out of the video. So it can be mapped to many or many-to-one. So we can get from a video a sentence. And similarly, we can have many-to-many transformation also. So recurrent neural networks have the following applications. That is image captioning, subtitle generation, time series classification, language modeling, natural language processing. Even chatbot development is also based on RNNs nowadays. So there is a major problem in the vanilla RNN. That is, if the RNN is having so many layers, so adjusting the weights at each hidden layer is a problem. That means once the information from X0 is transferred to A, it is multiplied by some weight matrix, then transferred to the next layer, then transferred to next, then transferred to next. And simultaneously, the output gets generated on the top. Now we have something called as loss function. That is the difference between the actual output and the predicted output. So if the loss functions for, say, ht plus 1 generates some error, so there's some like error of, say, 0.15%, and it's need to be backpropagated throughout the network. And backpropagating through a network that is so large is difficult because each time you can think of, say, W is getting multiplied at each layer, and multiplying W, that is between 0 and 1, multiplying anything by 0 and 1, between 0 and 1, say 0.2, if we multiply something by 0.2 multiple times, then it will be tending to very small value. So it will be like the gradient will be propagating through the whole chain, but it will be taking much time to train. So it is not feasible solution. So vanilla RNN suffers from the vanishing gradient problem. Likewise, we have the exploding gradient problem. So exploding gradient problem is when the value of W is greater than 1. So if you multiply simultaneously a number by, say, a factor of more than 1, then it will tend to always go and multiply to many huge values. Now, the vanishing gradient problem can be thought of as W is less than 1, and exploding gradient can be thought of as W is greater than 1. To solve these vanishing gradient problem and the exploding gradient problems, we use certain techniques. So for exploding gradient problem, we have truncated backpropagation. So in truncated backpropagation, we divide the whole set into certain batches. And in those certain batches, we just backpropagate within those certain batches sequentially. In system of rewards and penalties, it is like reinforcement learning. So we provide rewards for, say, if the backpropagation is doing well, else we provide penalties. And we have gradient clipping. If the gradient goes beyond some range, then we just clip that gradient and we don't propagate it through the network. For vanishing gradient problem, we have smart weight initialization that is like a guesswork. Then we have eco-state networks and we have LSTM. So I'll be talking today of LSTM, that is long short-term memory. And it is one of the most used variants of RNN. So LSTM is one of the most used variant of RNN. And the approach for LSTM is making the weight W equal to 1. So you can think of you are not having W less than 1, you are not having W greater than 1, so what else we can do? We can just make W equal to 1. Now, coming to the architecture of the LSTM, C is the new introduction in here. HT is the state of the current input, the hidden layer, and CT can be thought of as the cell state. So in here, if we provide the input XT and the hidden layer, and we transfer this thing to 4 states, F, I, G, O. F is the, you can say, the final gate or forget gate. I is the input gate. G is another gate. There's no name for it. And O is the output gate. We apply the function like the element-wise multiplication and the addition using this formula. So CT is basically F times, that is forget gate times the CT minus 1, that is the previous state, the previous state of the cell that was there. So it is basically forgetting some part of the memory. So it is like you were reading something and you actually forgot some part of it, but you retained certain part of it. So this is actually forgetting major part of it and retaining some part of it, and that some part is used for training the rest of the network. And this is actually applied through the tanh function, and the output gate is multiplied, and we get the output of the hidden layer. So comparing the RNN and the LSTM, it is, we can say the LSTM has a sophisticated architecture in terms that it has a cell state, and using this cell state, it is like a super highway through which W is not getting changed. So we are actually changing the element-wise fraction, that is F, and we are not changing the weight matrix. So multiplying anything by element or scalar multiplication is much simpler than the matrix multiplication, which is involved in the weight matrix multiplication that is used in the vanilla RNN. So that is why the vanishing gradient problem goes off in LSTM. Now, we can start building the LSTM, and the code I'll be providing for that. So you can just join in this. You can just implement this as it is now. I'll be just shifting to the implementation thing. So the major tasks of implementing the RNN involves the data preprocessing, then building the recurrent neural model, and making the predictions and visualizations. So before implementing, we need certain libraries, that is Keras library, then we use scikit-learn, we use TensorFlow, and yeah. So first task is data preprocessing. So we import the NumPy library, we import the matplotlib library, we import the pandas library. The NumPy library is for visualizing the results, is for array manipulation, matplot is for visualizing the results, and pandas is for managing the data sets. Because the Keras library, yeah, zoom, okay. Can you see now? Okay. So since the Keras library doesn't support the data frames of pandas, we need to use the NumPy arrays for Keras library. Now, before starting, let me introduce you to the problem. So today we'll be predicting the stock price for the Google for first month of 2017. So these are the records that you can see. These are the records that you can see. So these are 20 records. That is, each month has 20 financial days. That means weekdays. So this is the record that we have to predict on. And the training data set is this. So we'll be predicting the open stock prices of Google for first month of 2017. And we'll be training on the year 2012 to 2016, so 5 years of data. Now, actually, the prediction should look like this. So if I take these two columns and just insert the plot for it, so the result that we should predict should be like this. So today our task is to mimic this behavior of the stock price in January 2017. Now let's get started. So the training data set is, I'm calling it Google stock price train.csv. I'm importing it as a data set, the pandas data frame. So I'm using pd.read CSV. Then since this data frame contains many columns, but we only require the open stock prices. The open stock prices, that is column 1. So I use the iloc function for selecting. For the first parameter in iloc is the colon. That means it will be selecting all the rows. And the column, the second parameter is the column parameter, that is 1 to 2. So 1 points to the open, and 2 basically points to the next column. But since the second value is omitted, so it is just considering the first column, that is the open column. And dot values is for converting it to the NumPy arrays. So we are just converting the pandas data frame to the NumPy array. Now we need to scale this data, and we'll be using the scikit-learn preprocessing library. And from that, we'll be using the min-max scalar class. So SC is the object of min-max scalar class, and the feature range parameter here tells that you need to convert the values of the column between the range 0 to 1. So everything will be scaled between 0 to 1. And after that, we just fit and transform. So fit and transform means, fitting basically means normalizing the data. So it actually takes the minimum value from that column and the maximum value from that column, and it puts it, the transform puts it into the normalization function. The normalization function can be the standardized function or the normal normalization function. So in standardized function, we take the mean value and we subtract it from the actual value, and then we divide it by mean value. But in normalization function, we take the min value, we subtract it from the mean value, and we divide it by the difference between the max value and the min value. So it is a basic normalization thing that we are doing. So fit and transform does this thing. After that, we need to create the training data, the training list, and the predicted ground truth list. So xtrain is a list, an empty list, and ytrain is an empty list. That is for the training, you can say set, and the ground truth set. So we have 1 to 58 records here in the stock prediction data. So we have 1 to 58 records. These are 1 to 58 records, and we are taking the time step as 60. So what is time step? Basically, time step is a very important concept here in the recurrent neural networks. It is basically how many observations you will be taking into consideration for training the next value. Or you can say, if you are focusing on just predicting the ith value, then what set of values you will be taking into consideration before that ith value. So it is basically, I'm starting from the 60th record. It means it will be taking the data of 3 months, training on that, and predicting the 61st value. So it is just an assumption. You can take 20 days, 18 days, anything, but it is like during my testing, I took 60 and it produced great results, so I'm using 60 as the time step value. And 1 to 58 is the number of records. So I append to the empty list the training scaled values from the I minus 60th value to the current value. So that is basically appending. It is making an array in which one record contains 60 previous values from the current value. So it is like a you can say n cross 60 matrix that is getting created. Now the ytrain is basically the ground truth, and the ground truth will be just having the current value. So it is from I to I plus 1, and 0 is basically the column. That is the first column because we have already cleaned our data and we are just having one column for open stock prices. So 0 points to that thing. Now xtrain comma ytrain equals np.array, so it is converting to numpy array. So we are generating xtrain numpy array and ytrain numpy array. Then we need to reshape the xtrain array. So reshaping means that to work seamlessly with the, you can say, numpy arrays and the RNN stuff, we need to add an extra dimension to the this existing numpy array. So basically, this is basically xtrain.shape is the number of rows, xtrain.shape 1 is number of columns, and 1 is basically the indicator column. That is the open stock column. So we are just reshaping to build it a 3D array from a 2D array. Now the first step of data preprocessing has been done, and we are on to the next step of building the RNN. Does anyone have any doubt in this? Yeah. Yeah, so basically we need to train the data. We need to say we are having values, say 700, 800, 1000, to say 20, 22, 5 in the stock prices. And it is not ideal. It will take a lot of time and it will not generate good results if the data is not scaled between some values, say 0 or 1. So I have provided the range 0 to 1 to make it more cleaner. So it will be approximated to the nearest value. So it is just cleaning the data and smoothing the data. So scaling has that use. Yeah.
The xtrain for the amount of this, you chose 60 because,
yeah.
Because you could see the result was okay.
Yeah.
You can't see the result.
Yeah.
You don't know the result. How can you choose a better
Right.
number?
So basically, the question that you are asking is a very good question, and we use something called grid search for this. That is basically a part of hyperparameter tuning. So these are basically pointing towards the hyperparameter stuff. So 60 is like a hyperparameter only, which is making or which is amending how the predictions are being made. So what we can do is, after this is done, like this is the first go for you all people, but I tried it with certain parameters. And in the hyperparameter tuning, the grid search library provides you with, you can provide arrays of values. Say, I have something called, say, time step. So I provide time step equal to 30, 60, 300, suppose. And I have another value, say, optimizer. And I take 3 optimizers, suppose, which are used for this type of regression. This is a regression problem because we are dealing with the continuous values. So we take, say, RMS prop optimizer that I'll be telling you more about. And we take Adam optimizer, and we say N Adam optimizer. So it will be doing a cross product. So it will be take this parameter 30 time step, cross it with the first RMS prop, and generate result. Then 30 Adam, generate result, 30 N Adam, generate result. Then it will be doing same thing with 60 RMS prop, 60 Adam, 60 N Adam. So it will be generating 9 results. And from those 9 results, you can actually get the matrix formed, which will be showing which one is generating good accuracy and less loss. So using that grid search thing, you can actually judge which hyperparameter to tune to what value. So that is part of grid search. Yeah, thanks. No, I have not, because it is like, I don't have that much time for showing. Yeah. So now building the RNN stuff. So we are importing 4 classes, sequential, dense, LSTM, and dropout. Sequential class is for basically inputting the first, you can say, set of inputs to the neural network. Dense class is for the last layer of the neural network, that's the output layer. LSTM class is for making the hidden layers of the neural network. And dropout is for something called as dropout regularization, which I'll be telling you more about further. So we are making a regressor. Since it's not a classification problem, we are dealing with the continuous data set, so it's a regression problem. So we make an object of sequential class called regressor, and we add the first layer to it. So it's regressor.add. So regressor.add will add layers to the neural network. So first layer is the LSTM layer, the hidden layer that we are adding. And units equal to 50 means the number of neurons, you can say, that we are introducing to the network. So this layer will have 50 neurons. And you can take it any value. So it was, again, the hyperparameter stuff. So I took 50. Then return sequence is equal to true means that the output of this layer will be getting forwarded to the next layer. And input shape equals xtrain.shape. One that points to the columns of the data set, and one is for reshaping it to the 3rd dimension. So we are just using the column and the 3rd dimensional value for it. We don't need to use the first row dimension value for it. So this will be adding the first layer, and adding the first layer may introduce overfitting, say. So to deal with the overfitting problem, that is to, say, avoid the noise that is being created by the overfitting stuff, we use the dropout regularization stuff. So dropout actually means dropping out certain number of neurons from the layer. So out of 50, I have chosen 0.2, that's 20% to be dropped out. So it means it will be just considering 40 neurons for the next layer, and out of those 50 neurons, 10 neurons at random, or say 20% of those 50 neurons will be dropped out at random. So this actually avoids the overfitting problem. Yeah.
How does dropout work in several iterations? Because after like 5 iterations, I don't know.
Yeah, so basically it's a stacked LSTM. So I am using 4 hidden layers in this. And for the 4 layers, I'm adding 4 dropouts. So, yeah.
So you have more than 1 iteration, right?
Mm-hmm.
With each iteration, you drop 10 neurons.
Yeah.
But you replace them or you drop them
Mm-hmm.
forever.
No, no. It's like during the epochs. Epochs is basically how many times the full data will be propagated forward and backward to lessen the loss generated by, you can say, the gradient. So it's actually for the number of epochs, the dropout will be done at random. So dropping out means just not considering 20% of those neurons randomly in one epoch. And in the next epoch, it will again be choosing random 20% and then be not considering. So it's like a random stuff going on. I've chosen 100 epochs. So it's fully propagating the data forward and backward. And training is done 100 times on this data. So it's like for each epoch, it is generating some random value. It's choosing some random neuron, and it's dropping out 10 random neurons. So it actually avoids the overfitting problem in that way. Yeah. And then similarly, I'm adding 3 more layers. So this is regressor.add LSTM. Now you have added the first layer initially. So you don't need to provide the input shape because LSTM class already knows that what is the input. So from the second layer, you don't need to provide this parameter input shape. It will automatically take from the previous thing. And this is the second layer, then this is the third layer, and the fourth layer. In fourth layer, we don't actually need the output return sequence because we need to pass it through the dense layer and not another LSTM layer. So we'll be omitting the return sequence equal to true parameter. We can state here return sequence equal to false, but the default value of return sequence is false, so we are not putting here the parameter. And dense is the final output layer. So basically, it is the units equal to 1 means it will be having just one neuron. That's the resultant neuron. So dense is actually corresponding to the result of the neural network. Now, the building of RNN has been done, but the compilation phase is still left. Compilation actually means compiling with certain loss function and choosing the right optimizer. So as I told you earlier, RMS prop and Adam are the two optimizers that are used with RNN, and Adam is the one that usually works apart from, say, RNN also. It works with CNN also. So it is a much wider optimizer that you can use, and it gives good results. Again, a hyperparameter tuning thing. So I have chosen the optimizer as Adam, and since it is the regression stuff, so we will be using mean squared error loss function. If it would have been, say, the classification stuff, then we would have used the cross entropy or binary cross entropy loss function. Then we have compiled this, and then we are ready to fit it. So fitting the RNN for the training set. So we pass the fit function xtrain, ytrain, epochs equal to 100, batch size is 32. So it will be taking batch of 32. It will be dividing the data set into 32, say, element batches, and it will be working on those batches. It's again hyperparameter tuning stuff. So what I mean by hyperparameter tuning is that tuning the parameters of the classes in such a way that it provides good result or good predictions. Now, the task 3 is the prediction task. So we have done the RNN building stuff. We have done the data pre-processing stuff. Now is the task to predict the results. So actually, the data set for predicting was separate than the data set for testing. So we just take the test data set and we merge that test data set with the actual prediction data set to make it say a total data set which will contain every value. So here we are just converting the read CSV. We are creating a data frame of the test data set, and then we are again converting it to the NumPy array as we did it with the price, the prediction price stuff. Then we concatenate the open column of the prediction data set with the test column. So it will be 1258 plus 20 records. That's 1278 records in total, because during the time of testing, we need to consider the previous 60 records and for considering those previous 60 records, we should have a data set incomplete. So I'm just using this complete data set, and axis 0 is for vertical join. Input equals data set merged. So basically it is taking, it is creating another, you can say, NumPy array, which is based on the merged data set. And it will be taking the values, 60 values from the current state. So counting from 1 to 58, record number 1 to 58, it will be taking into account the previous 60 values to predict the results of the record 1 to 58. Now we are reshaping it again. And since we have already fitted the data earlier, we'll just be transforming it. So we are just taking the input NumPy array, and we are transforming the input NumPy array for making the predictions. And we use another list called xtest, and we append to this list the values from the last 20 rows that we need to test. And then we form the NumPy array of this, and we just shape it again, reshape it again. Now the prediction can be done using the predict function of the regressor class, the class that we formed. So regressor.predict basically makes prediction on the xtest list that we just formed, the NumPy array. And inverse transform is the function that is used to inverse the normalization stuff that we did. So now we are just, you can say, we are inversing the scaling that we did. We made the scaling from 0 to 1. We normalized the results from 0 to 1. We are just inversing the transform to actually convert them into the real value. So it will be something like 0 point something is converted into 770. That is, say, a stock price for one record. And then we plot these results. So since the time is short, I have already run this thing in PyCharm. So it was, say, 100 epochs. And you can see that I'll just show you, say, you see that with increasing number of epochs, the loss function is decreasing. So the value of loss is decreasing. So the loss must have started with, say, some value 0.3 or something, 0.0034, and it's now at the end of 100 epochs, it's 0.001315. So you can see as I'm going up, the loss function is increasing. So the value of loss function is increasing. It means that the training has been done correctly, and we have achieved certain level of accuracy so that the loss function has minimized its value from, say, it's in 30s or 40s, say 0.0030 to 0.13. And we can see that the plot that we have. It's following the trend of ups and downs of the market, but it's not actually predicting the correct values, though it is following the trend. That's like if the value of the stock price is going up, it is following that trend. So blue is the predicted one, and the red is the actual one. So using these parameters, I was able to generate this result. Doing hyperparameter tuning with grid search will definitely improvise these results, and it will actually match with some error with the actual red line. So it is like just following the trend with the red thing. So we can see that it is actually following the trend. So we can see on x-axis at 2.5, it is just going down. Then it's following the upward trend, and then it's being stable at the end. So it was this prediction that using these hyperparameters I was able to make. Yeah. So the source code for this, I'll be updating my slides, but it's on GitHub. It's at this address. I'll be just uploading my slides, and it will get uploaded on the session page. And after that, so these are my acknowledgements. Professor Martin Krishan, then my supervisors, Christopher Ola, for creating good blogs. And if you have any questions, then you can ask. Yeah. Thanks.
Thank you very much. We have time for a couple of questions.
Thank you. I wanted to ask, how did you tune your architecture? Why 4 layers?
Okay,
LSTM,
so when we deal with RNNs, we cannot go beyond, say, we generally choose 2, 3, or 4 layers, because it actually doesn't make any sense going beyond 4 layers, as the results will not improve over choosing 4 layers. So for just showing the implementation stuff, I used 4 layers, and it was just making some good assumptions when compared with using 3 layers or 2 layers. But generally in RNNs, we just don't go beyond 4 layers. It can be the case that if we are using RNNs with some other neural network, say CNN for, say, image captioning task, then it will be another scenario. We'll be getting the results of the vector generated from the CNN, and we'll be transferring those CNN results into the first hidden layer, that's the H0 thing. And those results will be just making further, you can say, vectors, forming vectors, which will then be propagated throughout the chain. So it will be having more impact on the RNN training, and in that case, we can just lower down from 4 layers to 2 layers, because it is already having lots of information from the CNN stuff. So it is basically based on that thing. So if we consider a basic example, that's the perfect roommate example that is very famous in field of RNN. If you have a roommate who cooks food for you, and he cooks, say, apple pie, chicken, and say anything, XYZ, anything. So on sunny day, he cooks, say, apple pie, and if it's another sunny day, then he just goes off the duty and doesn't cook anything. If it's rainy day, he's at home and he cooks next dish. So he cooks chicken for you. So it is like the first input is weather, that's sunny or rainy. The second input is the dish that he made previously. So these input provided to a state will predict the next output. So it's like a vector product plus the addition of some of the other things that goes in complex neural networks. You can just make sense out of it. Yeah.
Your GitHub repo, can you make it public as well?
Yeah. I'll be making it public. Yeah.
Okay, thank you very much again.
Yeah. Thanks. No, basically I applied the inverse transform function. So yeah. Yeah, it will be inside this range, but the results will get inverted. So the current value, so it will be inverse transform function. So that will be adding something divided by something that is lesser. So it will be just exploding the value from 0, 1 to scale of, say, hundreds. Yeah. Yeah, that is why the prediction is not predicting the actual result. It is having some variation with the results. Because you are using some smoothened value, and using that smoothened value, you are going to predict actual results. So these will have variations between them. Thanks.